Let's see here. Alrighty, quick mic check. Let's see if you guys can hear me. Awesome. Alright, so we're just going to hang out for a bit on this slide for a little bit as we're getting used to this new system. Alright, so as you guys can tell, I decided to go with a YouTube live stream. My experience with Zoom has been incredibly awkward. I don't know about you guys yet. Yes, how will attendance be counted? These lectures don't count for attendance. I'm going to have to be posting some kind of alternative. Let's get this kind of centered on me. All right, so the attendance issue. Here's my current plan. I'm going to be writing basically section quizzes. 2-3 question quizzes that go with every section we cover in the course. And if you complete them, that will substitute your attendance grade. All right, Mike, good. So the idea of this these section quizzes are to substitute the attendance grade. It's not a perfect solution, and I haven't finished writing them. So what I'll say is these things you need to know now. Watching these lectures live is not mandatory. It's not for an attendance grade because I cannot enforce everyone to watch these. There are going to be some students who now have jobs that want them to work. I've got a couple of students who are, honestly, their parents, and now they need to watch their kids. So, will this be available? Dan, when you ask available on Blackboard, do you mean these quizzes I'm going to write or the lectures? Because I'll just answer both. The quizzes, they'll be posted through Blackboard. Let's not talk about how great of a streamer I am, guys. Like you're kind of forced to be here for your classes. So, anyways, quizzes. I don't trust my Zoom privacy. All right. Sorry, I'm like reading your chat and trying to talk at the same time. So, coming back to point, quizzes. Quizzes will be on Blackboard. I'll have more information for it by the end of the week, guys. Honestly, I spent the most of last week getting prepared to do this stuff and, just taking care of, my family. So you'll have more information about these quizzes, and basically they're meant to substitute that attendance grade. I can't force you guys to watch these videos because some of you are going to be busy. Other questions I'm seeing. As I suspected, I see people have had not the best times with Zoom. So, so far, I'm hoping this is a good format. The downside of this is that you guys can't talk to me except through chat. But so far, that seems to be okay. Most of you seem to prefer typing your questions instead of asking this way. But we'll experiment. We'll see how the semester goes. Will we still be able to see your physics experiments? I don't know if I'll be able to do demonstration, guys. I don't know. I would love to. But I am currently not going to campus to get said experiments. All right. I'm glad to see people are liking this better than Zoom. But, so yeah, on the experiment side, I'm definitely going to incorporate them somehow. most likely what it's going to have to be is just I find other people's videos of the demos I want to do, because I don't have all the equipment to do it myself. So you'll still see the experiments in some way or another. It will not be me doing them, sadly. But it's definitely something that I'm going to miss. If it's something that I can do with my equipment, I definitely will. I will definitely be trying to find my own way to do it. All right. All right, so... Oh yes, good old YouTube copyright. So, as an educator, we're in pretty free territory about that stuff. I probably could play some copyrighted music for you guys and claim it's for class. How am I going to address the pass-fail option for grading that ODU is giving out? Okay, so I first officially heard about the pass-fail option around midnight last night. So I'm still learning the full details of the pass-fail option. My understanding is that it's entirely up to you to decide. Basically, so basically, there's apparently this option to say, I want this class to be a pass-fail option. And apparently by like April 27th, you guys get to decide if you want this class to be graded as a pass-fail or count towards your GPA. So if it counts towards your GPA, then like business as usual as far as I'm concerned. There's like 4,000 points in the course. You get your points, and I'll assign you a letter grade at the end of the semester. So from my understanding of the pass-fail, and guys, I'm going to be honest, we're going to have to look this up. We're going to have to check the school's policies on this, because this is very new to me too. My understanding is that if you choose the pass-fail option, it's basically if you get a C or better, you just pass this class, and it does not count towards your GPA. It should count towards your credit hours, but like I said, double check everything I'm saying right now. I only learned about this late last night. Alright, Trez is saying it gives you credit without affecting your GPA. Yep, that's my understanding of it too. Alright. So far, positive feedback. All right, guys, let's go ahead and try out our first lecture. So let's see. Let's start recording. So, welcome everyone. This is going to be our first online lecture of the semester for those of you. First online lecture for those of you who are on campus. For my online students, welcome to your first online lecture delivered live. My online students have mostly been watching these streams after I record them. So definitely ask questions. I've got the chat right here, so I can kind of see you guys coming up. And let's dive right into section 14. We're finally going into talking about starlight. All right. So I've broken this up into about 4 sections. We're going to talk about star brightness, talk about stellar spectra, and what properties we can learn from that spectra, and then move on to the HR diagrams. So let's start diving into our material. Let's start with a simple question. All right. I'm going to say, let's say I have 2 stars. All right. And we'll just let's say they are equal size to the best of my ability to draw stars. So they're roughly the same diameter or radius. All right. So we're going to have 2 stars. They're equal size, but they are different temperatures. And I'm going to say the blue one's the hotter star. I'm going to ask, relative comparatively, how does the hotter star radiation compare to the cooler star? And I see some star, cool, bad puns coming in from the chat. Right. I'm seeing options of A is one of them. Right. Or A is coming in. Yes. Repeat. Okay, so repeat this. I have two stars. I've got two stars. They are the same radius, same diameter, but one of them is hotter than the other. And so what's happening is the hotter one, because it's hotter, remember, you glow energy. The hotter you are, the more energy you're radiating off. So the question is, well, how does that affect, say, the number of photons? And everyone seems to have gotten it. Yes. The hotter star is going to radiate not just more energy because it's hotter, but it's also radiating more photons. So the number of photons coming off this, what we're looking at here is a plot of the wavelength of light coming off and basically the number of photons. So as you get hotter and hotter, you're giving off shorter wavelength photons. Shorter wavelength, higher energy. And correspondingly, the number of photons is starting to go up and up and up. So you're getting more photons radiation, and they're at higher and higher energies. So let's start talking about star brightness. And you've heard terms of like magnitude. So here's a great picture of this. We've got an asteroid, 65 Cybele. There's the asteroid. And it's labeled an apparent magnitude of 11.6. And here are two stars, HD 216932. It's got a magnitude of 9.1. And I go over here, HD 217121, apparent magnitude of 8.7. And you might notice they have these scales here, these apparent magnitudes, 8.7, 9, 11. These correspond to how bright they are. So let's start to tie all these concepts together. Take like that last picture. Let's say you're looking at a telescope, and this is the picture you see. You see a blue star and a red star. And the question I have for you guys is, which star is closer? I'm seeing a hard C. And there is no D option. All right. Soft C. All right. Everyone's picking up on this. All right. When we look at this picture, correct. There is not enough information to know what's going on in terms of the distance. All I see is the brightness, how big the star appears to me. And so there's a couple of ways to explain what we're looking at. So I'm going to rotate this picture. Every picture, there are three cases, so emphasis. This is the picture that we're seeing here on Earth. We look through the telescope and we can see this picture. Big blue, little red. Here are three cases of where those stars could be relative to us that all result in that same picture. They could all be the same distance, and one's just more luminous than another. They could have the same luminosities. The stars are equally luminous, but one's further away. And remember, the further an object gets, the smaller and smaller it appears. So they could have equal luminosities and just be a different distance. Or the most complex case, which is most likely what's going to be out there, is that they are different distances and different luminosities. You could have one star be a lot closer to us, but the other star is significantly more luminous. All three of these cases are going to result in the same picture for us here on Earth. So So what if we had multiple telescopes? We will get into this. One idea, this ties in the concept of, could I have multiple telescopes taking pictures of these stars? And the answer is yes, that will definitely help. 2 telescopes on the radius of Earth, basically we're on opposite sides of the planet, won't quite be enough to figure out these details for most of the stars universe. We'll talk about a concept where we use parallax, and we say, all right, Earth's over here at one time of year, measure out to the star. Now wait 6 months later, Earth has moved to the other side of its orbit. And there we'll stitch those pictures together to get these distances. So yes, using multiple telescopes is one way to expand our understanding of where the stars are at. So, we've gone over at least 2 of these definitions before, but I want to recap all of them together, all in one spot. So, you can have luminosity. So, a reminder, that is the total energy every second that is radiated by a star. The total energy. So, we're going to use this number a lot in later lectures. This won't come up again today, but we'll definitely see this value again when we start talking about other stars' luminosities. So when I say the luminosity of the sun, that's what the circle dot is. That's our astronomical symbol. L circle dot means the sun. And I'm saying the luminosity of the sun is equal to 3.846 times 10 to the 26 joules per second. And a quick side note, joules per second. Some of you might know this. A joule per second is equal to the unit of a watt, 1 watt. And so when you're looking at your text or you're looking online, you might see these values reported in terms of watts or joule seconds. They're the same thing. Right? So basically, luminosity is how much energy every second you're giving off. How much are you glowing? Then we talk about brightness. And brightness is scaled by basically the distance. It's not just how much energy the star is giving off, it's how much that energy hits us in a given area. Imagine trying to sunbathe, right? You're getting a lot of focused direct light, or is it scatter if it's long brought out? So you have to take into account the area. And so the brightness goes down with distance, right? And then new one, magnitude. Now I will point out that magnitude and brightness are very closely related to each other. They're very similar. Right? So the magnitude is basically the scale, and it's a measurement of the brightness. The magnitude, think back to the beginning of this bit, of this section. The magnitude is just going to be a number, 8.7, 11.2, right? It's just going to be a random number. It has no units associated with it. And the bigger the magnitude, lower the brightness. Right? So I've got a table on the next slide. Hopefully that'll clear this up. So we talk about stellar magnitudes, right? Let's go for Jupiter, Mars, right? These are the brightest planets in the night sky. Their magnitude is close to -2, right? Our sun is almost -30. And then you start going to the other side of the spectrum of this magnitude, right? Go to the faintest stars. Our eyes, our unaided eyes, we can see about a magnitude of 5.5, right? And more stars out there, their brightness goes down the further they are. And so the further away something is, the less bright it is, the larger its magnitude. So the larger the magnitude, the bigger the number, the less... Oh, come on, come back. Right. The larger the magnitude, the further away, or the less bright, right? Big magnitude, low brightness. Small magnitude, all right, we're into the negative. The more negative the number is, the brighter it is. So for our sky, the sun is the brightest object, which is why it has an apparent magnitude of about minus 27. Now, closely related to this scale is the apparent magnitude. Related to that is what's called an absolute magnitude. Remember, brightness and luminosity are related to each other. Magnitude is a measurement of brightness. So what absolute magnitude does is rescale all of this, all these numbers, to as if every object was the same distance from us. Basically, it says, take the sun, take the moon, Venus, Alpha Centauri, put them all 10 parsecs away from us and say, what would their magnitude be in that case? So this is, you could say, a fictitious number. It's a rescaling. Some scientists like to use this because this gives you a way to basically say the luminosity of the stars in one dimensionless number. Parsec. Parsec is distance. It's the distance of, if I have our sun, Sol, it's labeled a PC as a parsec. Hopefully this works. It's close to about 3 light. Let me double check the actual value. Let's see here. Yeah, 1 parsec is about 3.2 light years. So it's just a distance measurement. It comes from using parallax measurements, which we haven't talked about yet. We'll get to that around section 19. Right. So, an example of using this, right? Here is Sirius, right around here. The way you can find it, when you click on the picture, you zoom up on this. By the way, everyone, if you're following along the PDF, you should be able to click the images to link to wherever I got the figures from and see more information about them. So you can click, here is Orion's belt, over here is Sirius. All right. And so we have a relationship that can say, how can we compare brightness and magnitudes? So the way this works, take Polaris. Polaris, our northern star, has a magnitude of 2. Sirius has a magnitude of minus 1.5. Right. So going back to our idea of our magnitude scale, this is a lower number. It means Sirius is a brighter object. Sirius is brighter than Polaris. And so we want to compare these magnitudes versus their star brightness. Right? So what we're going to do here is say how much brighter is Sirius compared to Polaris. So we go to the formula, and I'm not going over the physics of where this comes from. This is actually an approximation, but it's a good one for our purposes. Right? I'm going to say, what's the ratio of brightness? How much brighter is Sirius compared to Polaris, the North Star? And it'll be this 2.5 raised to the difference in magnitudes. Right? Polaris is 2. Or sorry. Yeah, Polaris is 2. Sirius is a minus 1.5. So the difference in magnitudes is this 2.5 raised to the 3.5. And if you calculate that out, you'll find that this ratio, Sirius, is about 24.7 times brighter. Or another more straightforward way to say this, Sirius has a magnitude 1.5, Polaris has a magnitude 2. Sirius is about 25 times brighter than Polaris. So the emphasis, magnitude is just a different way to describe the brightness of the stars. And why do we still use it? Well, the magnitude scale was the first thing astronomers came up with. We have to go all the way back to the ancient Greeks. So, we can easily measure magnitudes. You just look up at the night sky, take your telescope, and you say, well, how bright is that object? Magnitudes are easy to measure. Now I want to talk about how can we go from magnitudes to luminosities. So emphasis. First step. If you got the magnitude of the star, that's equal to its brightness. It's just another way of saying what's the brightness. Now the brightness, how bright something is, well, it's equal to its luminosity over the area of the sphere. Or emphasis, this equation here. The luminosity goes as 4 pi r squared times the brightness. So what's this image they're showing here? Imagine I've got this star. Here's the source. It is bright, Polaris bright in our perspective because it is closer. I'd have to double check which one's closer. It's about how luminous these stars are. Remember that game of saying which star is closer, which one's more luminous? It's a combination of both. One star could be brighter but further away, or it could be more luminous. It's a combination of their luminosity and their distance. Right. So, coming back here, I've got my star, my source, and it's radiating rays of light. So each red ray is a photon leaving this star. Now, if we're close to the star, give myself a given area. Remember the emphasis. It's the amount of photons per area. If I'm close to the star, then the area is getting bombarded with tons of photons. So the star is going to be very bright. Then let's say we're further away. The number of photons starts to go down. Increase the distance. Keep the distance up. Right? Same area. And all three slices, it's the same amount of area, but the number of photons shooting through that area is going down. And this is what I mean that brightness goes down with distance. The star is the same luminosity. It's still spitting out the same number of photons, but the number we detect goes down as we're further and further away. But, once again, here's the emphasis. If I have the brightness, right, and I know how far away the star is, I can calculate how luminous it is. Calling back to the beginning of this, we said, here's the picture we see. We see a bunch of different stars. We measure the brightness. From the brightness, we get from the magnitude, we get the brightness. If we can measure the distances, we can calculate how powerful these stars is. We can say, hey, this picture that we see here is equivalent to one star. The red star is 1 parsec away. The blue star could be 2 parsecs away. Orange is 3. Right? We do this combination of connecting the brightness and the distances to get how luminous the stars are. And no, we have not covered how to get these distances yet. Someone in the chat started to pick up on it, of using multiple telescopes. There's a lot of techniques. We'll have an entire section dedicated to how do we measure the distances to the stars. But for now, I'll just ask you to take, we know how to measure that. Can brighter stars block out dimmer stars? Absolutely. The brighter stars can block out dimmer stars. We could toy around with the positioning of these stars such that this guy is literally blocking anyone behind it. And that is a big question. Can you resolve the stars that are close together and one's brighter than the other? It's a huge issue that scientists are constantly tackling. So, from this work, these are things, this is about the range that we've managed to figure out. The least luminous stars in the universe, There's something of about 10,000 times less luminous than our sun. That's the, remember, L sun is the luminosity of our sun. So we found that a lot of stars can be 1,000 times weaker than our sun, or 10,000 times. The most luminous stars, they tend to be about 1,000,000 times more luminous than our sun. So the range here is that you can be 10,000 times less powerful than our sun, or 1,000,000 times more powerful than our sun. So there is a wide range of stellar luminosities. But one thing we have noticed is that the majority of stars are less luminous. Majority are not that luminous. And so a big open question is, why is that? Why are most of the stars not that luminous? So there's a question of, is this these luminosities, are they less bright than the moon? It's the property of that distance thing. Our moon is going to be significantly brighter than most of the stars. However, because of the proximity, the moon is not as luminous as them. And someone's nailed it in the questions. Does luminosity affect your lifespan? Absolutely. How luminous you are affects how long the star is going to live. And that ties into this question of, why are most stars not that luminous? Well, the most luminous ones burn out the fastest. So let's segue into our next part, where we're going to talk about the stellar spectra. And we're going to talk about the stellar spectra. You guys remember this, O, B, A, F, G, K, M's. What do we mean by this? What is it? What information are we gaining from these spectra? So what we can do is define spectral classes, right? We can say stars are classified into spectral types. And basically what we're saying is, look at the spectrum of a star, right? And say the absorption lines. Well, the lines of absorptions. Here's some absorption lines. Right. Those lines are very dependent on the temperature of a star. So we say, look at a star, see what kind of spectrum it's giving off. From that, pull out information about its temperature and define this sequence, this O, B, A, F, G, K, M. Mnemonic to remember it: O, B, A, fine, Gus, and kiss me. That's how you remember this this spectral sequence. And this is basically a shortcut. What we're going to do is start putting stars into this categories so that we can cheat. You don't have to say, well, what star is this? I'd say, well, it's an O-class star. And that gives me a rough idea of like what its temperature is going to be. What kind of material do I expect is in that star? So that's why we define this sequence here. So on top of the OBFGKMs, on top of that, there's also a number scale, right? So we break our stars categorically by these letters based on basically their temperature. We'll delve into more details in a bit. But we also slap in a number scale. So perspective, I could have a O9 star. O9 is the coolest of a O-class star. Next in line will be a B0. OB is next. So a B0 is the hottest of B-class stars. Then I increment up. B1, go down. So the temperature is slightly cooling. B2, cooler. B3, cooler. All the way down to B9, where B9 is the coolest of B-class stars. And then, next category, A0, the hottest of A-class stars. Right. So, put in perspective, our sun is a D2 type star. All right. Furthermore, when I keep saying like our sun is an average type star, falls in the middle of basically all the scales we can throw at: temperature, size, luminosity output. Our sun is very much middle of the road, average. So some things we've learned, right? We could plot stars based on their spectral class or luminosity. You guys are going to see this plot again, so remember details like this. Right? We start to put stars onto this plot. And here are the things we start to notice. The hottest stars, when we talk about weak absorption, remember that spectral lines, right? We're talking about the spectrum. Right? Right. The hottest stars, they'll have a weak absorption in the hydrogen and helium. And these are going to be the type O's. Then you go into like the medium of the bandwagon. There's our good old Sol. Right? Our medium-sized stars, they're going to have strong absorption in hydrogen. That's going to be closer to like our type A's. And then keep going down, and you'll find your coolest stars. These are things that have absorptions in heavy elements. They're going to have sometimes molecules there. Right? So the type M stars are definitely the coolest, and they have the heavier materials in them. And you're going to notice a pattern of what kind of elements are present and the temperature of the stars. So remember way back, this was now a while ago, section 5, when we were talking about properties of light. How does light interact with matter? We said that if you have a spectral line, that's a fingerprint, right? I look at a star, I see the spectral lines of this. This is telling me what elements are there. They're telling me what is the composition of the stars. And by doing that, we've noticed that all stars are mostly hydrogen and helium, right? Look at this A1 star. You see this line here, right? Big line, big line, big line. This is what's called the hydrogen Balmer lines. First mathematically predicted all the way back in 1885. And the idea is that take a hydrogen atom, an excited hydrogen atom, and it will radiate these 4 lines predominantly. And so if you see these 4 lines, you know you have hydrogen. Well, look across the entire spectrum of stars. They all have these predominant Balmer lines. We see that all the stars are of a large composition of hydrogen. This line here is how we know that. These lines here are how we know that all the stars are predominantly composed of hydrogen. Because we see hydrogen in their spectrum. So, some more fun facts we see. In terms of our sun, we see that our sun is, by mass, about 75% hydrogen and about 23% helium. I'd have to specify by mass. If you say by number of atoms, the sun is like something like 90-something% hydrogen atoms. Yes, hopefully in some of your labs you got exposed to some of this. All right. So, emphasis here. We specify the spectrum of stars. We say, all right, look at the spectrum, put you in a spectral class, and shortcut. Because we've assigned you into your spectral class, we already have a rough idea of what your chemical composition is. What are you made of? This plot is basically the exact same information on the next slide, but plotted in a slightly different way. When I say like a B-class star, its predominant radiation is going to be something that corresponds to a helium, specifically neutral helium. Go to RG, you're going to see ionized metal, some neutral metals. Basically, we're looking at plots of what is the predominant source of radiation. What's the predominant spectrum glowing from that star? So this is essentially the same information on the previous slide, but plotted in a different way so we can focus on, like I claimed, that chemical composition. All right, sorry about that. So, just a little table to summarize all of this. Still choking my water, guys. I'm alive, I promise. All right. So here's our spectral classes again, and we can associate our sun, G2. Our sun's in the G range. Going along with, like, think about the color. We say our sun is a yellowish color. It's in the range of 5,000 to 6,000 Kelvin. All right. So I'll go with the top now. Our O stars. Our O stars, they tend to be a bluish color, and they're going to be incredibly hot. We're talking greater than upwards of 30,000 Kelvin. As you go down, we can see how the color changes. We go from blue to a bit of a white to a yellowish orange, down to the coolest stars that are glowing in a red. The M-class stars are around 25,000, 2,500 Kelvin in temperature. All right. So we're seeing what are the predominant materials in the star, and this goes back to why do we bother with the spectral classes? No. My wife tried to bring me a glass of water. Thank you. So, I'll repeat this. We have our spectral class, right? If we identify the spectral class, we have a shortcut. We can say, what's the expected temperature? What do we expect is composed in that star? What's in there? Now, as you notice, we have some more material down here. We get these LTYs. I didn't talk about them before because these are relatively new, right? We have our sun here, and we start to go further down the scale to an M star that's red, down to these cooler, smaller objects. We started discovering these things about 30 years ago. We started finding objects that were cooler than the class M's. And it turns out that's going to be things like brown dwarfs or some very high mass planets. So these things are not as bright or not as hot as a lot of the stars. Brown dwarfs are often described as failed stars, or a little bit different than that. All right. But the point is that we've had to, in recent history, recent for astronomy standards, expand our spectral classes. So I'm seeing questions of what techniques did they use? Basically, we got more and more sensitive equipment. We started to get bigger telescopes, and we could see further out there. It goes back to the brightness scales. Let me pull that up. So think back to those brightness scales. Here's the limit of what the human eye can see. Here's the limit of what a 1 meter sized telescope. Look at Hubble and Keck. All right. So we're starting to get better and better resolution. We can see dimmer and dimmer objects. So what's basically happened in the last 30 years is just we've gotten bigger telescopes. We've gotten a better ability to resolve the big objects. And that's how we're able to find these cooler objects. We just have improved our technology enough to resolve the smaller and cooler things in the universe. All right. So we're seeing more objects out there. We're seeing more stars. Well, what properties can we pull from this? Not just, hey, this is what it's composed of. That's one of the exciting things we can do. But we can say things like, how fast are they rotating? Like, for comparison, here's our sun. Our sun does a full rotation in about 30 days. Whereas you can look at other stars, like the star Altair, that'll do one rotation around its axis in about 6 hours. So we're talking about these massive stars that have these rapid rotations. So everything we're going to discuss in this part is going to be what properties can we learn about a star. So let's start with a simple idea. I want to know how big a star is, but I'm going to claim to you, we cannot measure the diameter directly. And right, I won't hold on to this for too long. Why can't we measure the diameters directly? They're too far away. Right? They're just too far away. These things are too tiny. We're not going to resolve. Even the best telescopes out there, you're not going to be able to have this perspective because you need to know the distance and how big your image is. So we're going to have to use other tricks. We're going to have to use other tricks to figure out how big the stars are in the universe. And I'll make this picture a little more complicated, but I do love this. So let's go back to that game again. All right, so let's consider two stars. This time I'm going to say the stars, they are the same temperature, but they're going to be different sizes. Hold on, I'm seeing a question. Do all stars have coronas? And that be a part of the diameter? Excellent. So yes, all stars will have an equivalent of a corona. Now, how far that corona, that atmospheric layer, expands will depend on the properties of basically how massive that star is. In terms of diameter, for stars outside of Sol, we tend to define the diameter as being the chromosphere layer, that surface layer. Right. So back to the slide. We'll have two stars. I'm going to say they have the same temperature, but one is a white dwarf, about the size of Earth, and one is going to be a blue giant, this gigantic mass star, hundreds of times bigger than our sun. So these two stars, tiny little object versus the big massive one, same temperature, but very different sizes. And so we'll look at the spectrum, and you notice the bands. All right, hold on, I'm seeing a quick question. Do hotter stars tend to rotate faster? I'll have to look that up. That is a tricky one about what patterns we've seen in stars. Wish I had a prop with me, but there's definitely correlation to how gravitationally massive you are and how quickly you're rotating. And as the gravitational forces get stronger, the more massive something is. Think about Kepler's laws. You do start to move faster just because there's these greater and greater forces acting on you. So there's definitely a relationship between mass and rotation rate. Right. So come back to the bands. Same temperature, different size. Look at how narrow the bands are for the big star versus how wide they are for the little star. Right? So the narrow bands, think about this. The giant star, because of how big it is, that outer layers, they're going to be a lower pressure, low compared to this guy. So the giant star, because its atmosphere is spread out so wide, you're going to have more narrow spectral lines. Whereas the tiny star has this huge, remember the pressure, it's just squeezing it in. Right? That squeezing increases what we call energy bands, the range of allowable energies. So by increasing the pressure on the tiny star, the bands that are radiated or absorbed are going to be wider. So we're comparing two stars of the same temperature, and the difference in their bands is allowing us to infer the size of the stars. The spectrum's not just telling us the composition, it's telling us how big the stars are. Now let's try and actually calculate the size. Here's one technique to do it. So once again, I'm going to do the game. I'm going to have two stars. I'm going to make them equal size, but different temperatures. Those stars that only emit outside the visible spectrum. So, all right, I'm seeing requests for me to go back a bit. So let me answer the question. Are there stars that emit only outside the visible spectrum? So let's think back to this picture, right? The star is going to radiate in an entire spectrum. You're actually going to have the visible spectrum, let's see here, way out here. And so the star is irradiating in this whole range, but the bulk of their wavelength is going to be outside. So yes, there are stars that will have ultraviolet glows. You'll have stars of X-ray stars. We'll talk about stars that are glowing the X-rays. So you can have this wide range. All right. So I saw a request to explain this again. So let's go through this. Big star, all right? Big star, low pressure. Low for stellar sense, low compared to this guy. So big star, less pressure, more narrow spectrums. These lines are more narrow. Go to the tiny star, these bands are going to be wider because there's increased pressure, there's more energy gaps, right? Basically, the amount of allowable absorbable energies start to go up as I squeeze and press on these things. So these bands, they tend to get wider. So the emphasis here, the length of these bands, they are slightly dependent on the size of the star. That's the emphasis. I can look at two star spectrums and infer how big the star might be, or at least compare their sizes. So let's try and get a more formal way. Let's actually try to calculate the size of stars. So this time, two stars, they're going to make them the same size, but different temperatures. How can you tell the temperature again? So I will get to that in a little bit. There is a way for us to get the temperature of the stars. It's based on the peak. You're going to see that that curve I did earlier at the beginning of this lecture. You'll see that again. So you will be able to get their temperature. Emphasis. I'm going to say the blue one is the hotter star. So if I look at just one section of the star, hotter star, it has to radiate more photons. It has to give off more energy. It's a hotter object. So the hotter object has to be giving off more energy per area. Well, if there are more photons coming out of this star than this one, then this guy must be more luminous. So here's the emphasis. If I know the luminosity and I know the temperature, I can get the size of the star. Right? We talked about in our previous parts how to get the luminosity. You go magnitude to brightness. If you know the distance, you calculate the luminosity. Now, we just need to get the temperature. And then I'll get to your question. How do we get the temperature? It comes back to this plot here, right? Here's the thing. The temperature of the star. Stars, all of us, we're called black bodies. We all radiate equivalent to what's called a black body radiation. We give this whole range of wavelengths that we glow in. The shorter the wavelength, the higher the energy. As the object gets hotter and hotter, it's going to radiate in more and more peaks, right? There's a peak wavelength, right? Here's an example. I'll draw this one. Here's the peak wavelength of this object that's at 4,000 Kelvin. Or the peak wavelength of this guy at around 5,000 Kelvin, right? So if you can measure the peak wavelength, if you get that peak wavelength, then by what's called the Wien's displacement law, that's this guy, you measure the peak wavelength and you do 2.9, 10 to the minus third meters Kelvin per that wavelength. You calculate the temperature. So you measure that peak wavelength. Look at this. By finding the peak wavelength that star is radiating, you know its temperature. And this ties into what we call the Stefan-Boltzmann law. And here's how it goes. We say, look, the luminosity, the amount of energy a star is giving off, well, it's equal to the surface area of the star, 4 pi r squared. 4 pi r squared. That's the surface area of a star, or r is the radius, the diameter of the star, if it helps people. Here's my star. There's my radius. Right. So if I know the radius, right? Well, I want to find the radius. I can find the luminosity from techniques we described before. I can get the temperature by knowing the peak wavelength of light emitted from it. Right. Here's a plot of that temperature luminosity dependence. The sigma here is called the Stefan-Boltzmann constant. And simple math, I just rearrange this formula and I get the radius of a star. It's just dependent on the temperature and the luminosity. And this is the game that we're going to keep playing. What information can I measure? What information can I calculate from that? So we've gone from magnitude. We've gone all the way up to, from magnitude, we can get how powerful the star is. By looking at the spectrum, we can get how hot the star is. Well, now I know how powerful the star is. I know how hot it is. I know how big the star must be. So we're just pulling more and more of these stellar properties out this way. Some other things that we can learn using our spectral lines. We can measure things like what's called the proper motion of a star. Get an idea what I mean by proper motion. A star could be coming towards us or away from us, and we'd measure that using Doppler shifts. Is the star like blue shifted, red shifted? That can tell us if it's coming toward or away from us. Or the proper motion, let's say we're here, is the star transversing? That's what I mean by transverse. Is the star moving this way at all? This motion, right? This motion we can easily tell. The star is coming towards us, blue, away, red. By looking at the spectral lines, we actually can learn about its transverse. We can learn how it's moving across the sky. Put this in perspective. Here's the Big Dipper about 50,000 years ago. And about 50,000 years from now, this star is moving towards the right. These stars moving to the left. The Big Dipper is actually going to start unfolding. So you might notice the difference from this image to this image is 100,000 years. So we're not going to live long enough to measure proper motion, or at least for our meek eyes to be able to see it. But by looking at the spectral lines, we can calculate the proper motion of the stars. That's what these arrows are showing us. These arrows are showing us which way the stars are actually moving. And with that, we can calculate what the constellations will look like in thousands of years. Now we can get, coming back to that rotations, we'll focus on the non-rotating star first. It's radiating a certain amount of light. And that light comes down to us, and we see a spectrum. We see the peak, boom, we've got the properties of the star. But if that star is rotating, look, some of the photons will be blue shifted, some will be red shifted. Yes, there is a color shift. There is a slight shift for the stars moving left or right. There's a slight shift in the spectrum for a rotating star. So we see, in this picture, we see the band has widened up a bit. We can see the band is widening up. So the peak, instead of being a nice big dip in the center, it's this lazier one. And so we can say, well, the widths. Measure the widths of these gaps. These widths gives us information on how rapidly that star is rotating. Now, before anyone types it up, I can just sense that these questions are coming. We've talked about the narrowing, the spreading of these spectrums. Of how wide is this? Didn't we just say before that it could be due to the size of the star? It could be due to its rotations. The full answer is, it is a complex combination of all of those stitched together. And it's our job as scientists to sit down and pull apart. Is it the rotation? Is it its distance, its size? It's our job to pull all this together. Right. This is how we know Polaris will no longer be the North Star. So there's a question of going back. Is properties like this why we know that Polaris will not be the North Star? Almost, but actually, this is not the main reason. Let me pull up my little drawing piece here. All right. Here's Polaris, my very poor drawing of Polaris. And here's Earth's axis of rotation. Let me get into... So Earth is rotating... So these who aren't following, the question was, is the proper motion why Polaris will not be our North Star forever? And it's not quite that. So Earth is rotating this way around on our orbital axis. But what's going to happen in about 20,000 years is that Earth's rotation axis, right? Here's Polaris again. What's going to happen is that our rotation axis is going to tilt. Earth has a tilt in its motion. So it goes from rotating this way to this way. And basically the tilt in our rotation changes. And that's going to be why Polaris will not always be our North Star. It will sometimes be our North Star, and in a couple thousand years it'll be another, and eventually it might come back. All right. I love the questions that are coming, so please keep sending them in. Will that make our seasons more extreme? Will this tilt make our seasons more extreme? It definitely is a factor into the seasons. You can talk about how Earth's seasons or Earth's climate has changed over the millennia. We're talking geological timescales. And yes, Earth's tilt like this does have a slight bearing. Right. So, continuing on. Properties we want to measure. How do we get the mass of the stars? How do I weigh it? I can't pull out a spring scale and put the star on the scale. So basically, there are two methods I'm going to talk about, right? One method, we look at the spectral class, we figure out what's the star composed of. I know there's hydrogen, to about this amount, helium, I know there's some calcium. Say, what are its components? How big is the star? Add up its mass, calculate its mass. You just say, how much is there? How big is it? There's its mass. Another technique, if we're lucky, is we can study binary stars, two star systems. So we're talking about two stars that are orbiting around each other. And think back to satellites, right? If you put a satellite in orbit around something, you can calculate the mass of the thing that's being orbited. And here's a very similar trick. I say here are two stars. They're orbiting around each other, and I can start using Kepler's laws to start pulling that information out. So we're going to have a couple of different categories of what we call binary star systems. Emphasis, binary, I just mean it's two stars in orbit around each other. One of the categories we'll call our visual binaries for hopefully what's obvious. We can resolve the stars separately. We can actually see the two stars around each other. So let's go through this, all right? Basically using Kepler's laws. You're going to have a high mass star and a low mass star. They're going to orbit their common center of mass. So they're doing big orbits around that center of mass. So you look at Doppler shifts, right? You look at Doppler shifts in those stars' velocities, and you get how quickly they're moving around. From that, you can get the total mass of both stars, how quickly they orbit their center of mass. And so from this, we've got an idea of like the range of stellar masses, and we found that the lowest mass stars are about 0.08, about 8% the mass of our sun. Remember, circle dot is Sol, our sun. So low mass stars are about 0.08. The high mass stars are about 150 times the mass of our sun. So, other types of binary star systems we found out there. You can have spectroscopic binaries. So these stars, they're too far away. We can't separate the two. They're too far away. So they just look like two objects stacked on top of each other. And what we can say is, well, we can just do the spectroscopic shifts. We can't visually see the stars apart, but we can see these spectral shifts. So as the star is rotating, here's A. As A approaches us, it'll be blue shifted. And then, all right, so 1, 2, 3, 4. Follow star A. A is blue shifted. Basically, no shift in A. And then as it goes away, A becomes red shifted. And repeat. So, how do I measure the speed of these stars as they orbit each other? Well, you measure, here's the A as it moves around in the spectral line. You measure the change, the frequency of this rotation. And by measuring that, you get, well, how quickly A and B are orbiting around their center of mass. All right. I'm seeing a question on what are black bodies. Okay, quick answer. A black body is any object that's interacting with light. We are glowing photons right now. So a black body is to say that I am absorbing photons, I am emitting photons at an equal rate. All right, binary stars. Binary stars, two stars orbiting each other. That's what I mean. Binary stars means two stars in an orbit around each other. I see a question. Is it possible for A to block out B? Literally our next slide. So let's move on to that. So I'll go back a bit to summarize. Binaries we've talked about. Here are two stars orbiting each other. These would be visual binaries because we can see them. We can tell them apart. We have spectroscopic binaries. These stars would be too far away. We can't resolve them apart. But by measuring the spectral Doppler shifts, by measuring this Doppler shift, we're measuring how quickly they're rotating around each other. Now someone asks, well, could one star block the view of the other? Absolutely. We call them eclipsing binary stars. So let me pull up the little GIF here. All right. There we go. All right. So, what do I mean by eclipsing stars? They're rotating around each other and they pass in front of each other. So what's going to happen? All right. And our simplistic model will say, well, it's one star is going to be a lot bigger than the other. And as the smaller star crosses in front, it eclipses the other. As that eclipse happens, it's going to reduce the brightness of the star. Right? So as one star is going in front of the other, the brightness goes down. Then you can see them apart. The light curve goes to the top. And then one goes behind, the brightness goes down again. So you measure the time. You measure the time between these dips. That's telling you the period of rotation and how deep these dips are. How deep these dips are? Well, that's related to how big the stars are. So the period is telling you how far apart the stars are. The dips are telling you how big the stars are. So, stitching all this information together, we're starting to pull plots of all the stars we see. Here we have a plot of mass in terms of solar masses and the luminosity. And we've noticed a pattern. We're starting to see patterns here as we do these types of measurements on all the stars we can see. We do that. We found about 90% of the stars follow this relationship. About 90% of stars follow this relationship. And it's approximately that the luminosity of a star is proportional to its mass to the fourth power. Another way to phrase this. If I know how massive a star is, I know its luminosity. And the symbol here, this is similar, right? This is not an exact relationship. It's not an equation. But there is this relationship that exists here that by knowing the mass of a star, that's giving me information on its luminosity. All right. So here is a brief recap. I'm not going to read the slides. I'll leave that up for you. But just a quick summary of like the different properties, stellar properties we could find, and the techniques we've used in order to get them. All right. Get some water. Oop! I still have the. Let's take that away. You guys didn't warn me the gift was still playing. Alright. So we'll get into our last bit. We're almost done. Alright. We're going to have our HR diagrams. And so you're going to see plots like this a lot for the rest of the semester. So what are HR diagrams? They're named after the scientists Hertzsprung and Russell. And the idea is simple. If we plot the spectral class, or another way to put it, the surface temperature, versus the luminosity of the star, where do the stars fall? Where do the stars fall in that pattern? And we're going to notice characteristics. We're going to notice what we call things like the main sequence stars, giants, supergiants, dwarfs. We're looking at where stars fall on this Hertzsprung-Russell, or HR diagram. You're going to see a lot of different ways to plot the X and Y axis. On the X axis, we can put spectral class, we can put temperature, we can put peak wavelengths. There's a lot of different ways, but they all represent the same thing. Effectively, the temperature, where this is the hottest and this is the coolest, versus the energy output. So, for starters, we said about 90% of stars follow that L is into the fourth pattern, right? That's what we mean by the main sequence. And to put in perspective, why discuss... Here's the main sequence, right? There's your main sequence stars. Why do we care about those? For perspective, we can talk about an analogy with humans, right? Take a sample. Let's say I sampled everyone in this lecture right now. You told me your weight and your height. Most of us are going to fall on this main sequence of humans. We're all going to fall into this main sequence where the taller we are, the bigger we tend to weigh, with there being outliers in both directions. So we can say most follow the main sequence. The same thing applies to stars. Now the emphasis here, an important thing that we're going to build up here, is that the main sequence stars, where a star falls on the HR diagram, it's going to tell us about that star's life. So, look at our main sequence, O, B, F, G, K, M's, right? These are the main sequence stars. They're going to start from high luminosity, high temperature. They're going to go down to low luminosity, low temperature. Yes, our sun is on the main sequence. And here's the emphasis. If I know the star's spectral type, I know which one of the categories the star falls into, and I know where it falls in the HR diagram, this is actually a way for me to calculate its distance. The actual technique is called spectroscopic parallax, and we will delve into this detail later on, around section 19. But we will talk about how I can use the spectral type and its position on HR diagram to get its distance. And I've said this before, and this is going to really start applying a lot now. Knowing the mass of a star helps us predict where in the HR diagram it falls and what its life cycle is going to be. So, not all stars are going to be on the main sequence. We can talk about the giants, how a star can go from on the main sequence to leaving the main sequence. And you're going to get some weird examples here. Some stars are going to be very cool, right? Remember, this end of the spectrum is the coolest stars, but the higher up we go, the more luminous we get. So we're going to find stars that are not that hot, but because of their volume, how big they are, they're going to be very luminous. So the star will be cool, but it'll be brighter compared to other stars just because of how giant it is. And the opposite exists. We're going to have very, very hot stars that are not very luminous because these stars are tiny, compact. So there's definitely a relationship between how luminous a star is and its size. All right. So, summary of what we've talked about so far. We know that there's a relationship between luminosity, brightness, and magnitude. We're going to start talking about stars of where they fall on the stellar spectra. Remember, O, B, A, flying, Gus, kiss me. Right? And from these things, we've talked about how to measure all sorts of a range of stellar properties. And with those, we're going to start plotting stars on these HR diagrams, these Hertzsprung-Russell diagrams, and start discussing their stellar evolution. All right. So, hope everyone enjoyed these lectures, and we'll see you next time. Whew. Not an acronym, mnemonic. Let's see if I can spell this. All right. Absolutely. All right. So I'm going to stick around for 5-ish minutes if people have questions either on material or about courses and all that stuff. So I'll stick around here. Go ahead and send me chats. Yep. See you next class. So our next test will be this Thursday. All right, so I'm going to answer test questions now because I saw those coming up during the lectures and I just ignored it because I wanted to wait till the end. So next test. It will, if you are an on-campus student who has now become online, it will become available to you Thursday at 1:30. Yep. Yeah, I'll become available Thursday at 1:30. You'll have 75 minutes. It's going to be the same format as the last one. About 45 multiple choice questions and one written problem. The main difference, open notes. It's going to be an open note test. I'll be frank, it's not worth the time and effort for me to try and figure out some sort of proctor system, at least for this test on Thursday. So open notes, it'll be sections 6, let's see here. I'll type it in. Sections 6, 7, 13, and a little bit of this material that we just covered today. Let's see here. How our honor portion is going to work, how the lab portion is going to work. Okay, so honor students, you still have your honors projects. So you'll still get your papers to me by, I believe I set the due date to be this Friday. As for labs, The labs are still up in the air. We had a backup plan, and then when they basically barred campus from almost everyone, our backup plan kind of fell apart. So we're still figuring out our backup to the backup plan. So I do not have a direct answer for the labs right now. Yes, the lowest test grade is still being dropped. All right, I'm going to answer these in the order that I see them. Can the test be taken only during the class time? No. The test will open Thursday at class time and be due probably by like Friday night. And that's just because I can't expect everyone is available at that time. Some people are, honestly, they're working. Others have to share their computers. Others don't have stable internet. So I can't force everyone to take it at the same time. So it's going to be like this weird like 30-ish hour time range that's available. All right. A few students are confused. So a few students are confused about the lab portion because they still require certain equipments. Okay, so I'm responding to Destiny Williams right now. Confused by the lab. So, confused by the lab portion because there are still require certain equipment. So, here, Destiny, have you received emails from your TA or the lab coordinator, Justin, in the last, 5 days? Because right now my answer in the labs is I am uncertain for astronomy labs, especially a lot of these. Some of them can be converted online easily, others cannot be because, as I mentioned, the equipment stuff. So I'll be honest, I do not immediately know the answer to the labs. All right, I see some discussion. Are there going to be no more labs? Jude, I don't know. I don't know what we're planning for the lab situation. Like I said, we had a plan, and then because of changes due to just basically how rapidly the virus spread, our original backup plan got destroyed. Right. So let's see here. No more labs. We still. Let's see here. There will be one attempt on the test, 75 minutes. Correct. It's open notes. So yeah, open notes, open books. I have no comment after that. I feel like I missed a question. So these section quizzes. Not today. Basically, I'm going to write them in bulk and post them all at once. And so my goal is to get the quizzes up by the end of this week. And by then I'll also email how I expect it to work in terms of fixing your attendance grade or whatever. How exactly I'm going to incorporate that. So nothing quiz-wise now, in terms of like these section quizzes that are substituting attendance grades. Expect an update by the end of this week, and you'll have plenty of time to do them. So there are practice tests on Blackboard. If I recall correctly, the practice tests will have some section 15 material that will not be. Yep, thank you, Kiana. Let me double check the website. Let's go to... Yeah, go to the website, test material. Yep, a lot of questions about the sun. Yeah, so the practice test should be pretty good. Oh, I have no idea what we're going to do for a final exam. I'm not laughing to make fun of you. I'm just laughing because it's like, oh gosh. I didn't. None of us expected the world to shut down. So I don't have an idea how the final exam will be delivered, because in terms of like, can it be proctored? Probably not. There's too many of you and online. So as much as you guys are hoping for that automatic A, this is exactly why this idea of this pass-fail option exists for you guys now. So no, there's not an automatic A. You do have the option of making this class pass-fail, and I'll have to double-check the rules, but from my understanding, basically, if you get a C or better in the course, you just pass, and it doesn't affect your GPA. No lecture on Thursday. That time, like I'll make myself available to like answer questions. When will the gradebook be updated with homework grades? At the end of the semester. If you go to Sapling Learning, you can access a gradebook on Sapling, and you'll see your homework score there. And basically at the end of the semester, I download that gradebook and add it to Blackboard. Yes, pass. So apparently there is an option to elect your courses to be pass-fail instead of counting towards your GPA. So I will highly encourage you to double-check the forums. Let's see if I can find material. OU pass-fail academic policies. Let's see if it's been updated. No, that's not it. Alright, so I'm not certain where that information is. We'll have to find it. But basically, here's how the policy is going to work now. You can choose to have this course count towards your GPA, in which case, treat everything basically as normal. If you get a B, that's 3.0, C, lower and lower, right? So it can count towards your GPA, or it can be just pass-fail. You get a certain percentage. I have to check what that cutoff is, but if you get a certain grade, then it doesn't affect your GPA. You do receive credit for the course. So right now, that is not a decision I make. That is a decision that you have to make. You have to email the registrar or something like that. It's like I said, these policies, at least for me, was only officially announced last night. I knew it was coming, but I didn't know what the policy is yet. So either way, you have two options. Treat this class as normal. It affects your GPA. If you get an A, great, boost, B, C, whatever. Like it affects your GPA. Or it's just a pass-fail. You get the credits, but it doesn't help or hurt your GPA. And that's your decision to make. All right, so let's come back here. No homework's gonna be due this week. I'll move the homework due date. Alrighty, so I think that about wraps it up. I still see there's about 40. Yeah, people are starting to sign off. All right, so I think I'm going to end it here, unless there's any last second questions to be sent in. Otherwise, I'm going to call it a day here. Enjoy your days. I explicitly avoided making any coronavirus jokes or comments. I saw some people did it in the chat, but I'm hoping to treat this class removed from that and trying to have some sense of normalcy despite lecturing this weird way. So if that's it, if there's no more questions, I hope everyone has a good day and take care.